the organization of all this material that I think that is going to be very nice once we finish. But again, for anyone who is attending the individual talks. So I'm going to try to give you an overview of what we know and what we expect to know in the next years or decades in the future about the immense diversity of exoplanets, but also having a much larger view, because one of the things that we are now trying to put in context also is the diversity of the systems as a whole thing. In any case, there are many questions that we are trying to answer. Here you have a collection of them. Of course, it's not complete, but we are trying to enhance our knowledge about these different fields. And as you know, is one of the most active now, at least in the astrophysical and astrobiology fields of knowledge. We can say that we are in the golden age of astrobiology. So first, I'm going to describe a few methods, not all of them, the main methods that we have used to identify planets beyond the solar system and to try to gather information about their properties. So here we have a short collection of them. The radial velocity was the method that was used for the very first time to identify a planet around a solar-like star, almost 25 years ago, in 95. And transit spectroscopy is being used now in a very effective way, but these methods are not the only ones. We have other things. Essentially, what we are using is the small light, the little light we get from the star to detect any kind of indirect effect that a planet or a solar planetary system can have on the star. But in some cases, we can see the planet in a direct way. In any case, each method has its own limitations and provides different kind of information. But it's true that when we combine the first two, the radial velocity and the transits of the planet across the stellar disk, then we have a very nice information, not only the mass, but the radius, and we can have all the kind of information, and I am going to describe eventually some of them. The bottom line of this is that we have passed from the first stage, that is the discovery of the first planets, to full characterization, from formation, evolution, the composition, the atmospheric studies, climatology, habitability. Because as I will tell you at the very end of the talk, the golden piece of all of this is to try to detect an Earth-like planet and to verify whether we can confirm the presence of a biological activity. So you can see here different collections of methodologies. We can, from a general perspective, we can cluster them in three different kind of techniques. Spectroscopy is essentially, you see when you see the rainbow is the spectrum of the sun. So we use it to detect signatures that are hidden in this information. We can get direct image, and we can also analyze the light as it comes in the light curve of the star to detect different kind of signals. So there is a complexity behind of all these methods in details. I'm going to give you just some brief notes about some of them, but each of them can reach different kind of planets in different situations. So the goal now is to try to use as many of them as possible to complete this immense puzzle that we have, and to try to put all the pieces together and to understand, as I said before, how the planets and the planetary systems are formed, what are the properties, how they evolve, how many Earth-like planets we can find, properties of the atmosphere, etc. One of the main problems we have is that the geometry of the system is not very complex, but we have a limited access to what we see. So the planet is going around the star, but what we see is normally projected on the plane of the sky. So there is an angle, that is this eye that is highlighted, that is going to be crucial for many of the methods, and it's going to bias some of the results. So it's one of things we have to keep in mind that in some cases we don't get the full answer, and in some cases also it's an upper limit on what we want to know. So without further ado, I'm going to start to describe several of the methods. One of the most effective now, and probably is one of but it's difficult to say that it's going to be the best in the future, but it's going to be a protagonist without any doubt, is the transits when the planet crosses in front of the star or goes behind the star. We can detect a difference in the light that we get. It's just a tiny drop in the luminosity. When the planet goes in front, this drop is stronger. But in some cases, also when it goes behind, we also can detect this diminution of the light. And there is a periodicity in this phenomenon, and tells us the information that is behind this can tell us a lot of things about the geometry and the properties of the planet. In fact, most of the information comes from the study of the primary depth when the planet goes in front of the disk of the planet. And what we know, we can derive directly, is the ratio between the size of the planet and the size of the star. So one key thing that I'm going to repeat eventually also is the properties of the star. We cannot get information, or at least we cannot get accurate information about what is going on with the planet or with the planetary system if we don't have a more or less complete information and knowledge of the properties of the star. So both things are going to be very connected. And these are fields that actually link different kind of knowledge, not only in astrophysics, in other fields related with astrobiology. And just to emphasize this thing, to emphasize this ratio between the size of the planet and the size of the star, this depth, this small diminution of the light that we get from the star is related with the relative size. It's not the same when we have a very big star with a tiny planet, or vice versa. Sometimes we have a very small star, a red dwarf, we call it, and a giant planet is crossing the disk, and this diminution of light is going to be more important. So is this the way how we get how we can derive the planet size? Again, is because we know many things about the star. And in fact, if we put this mechanism in perspective with the solar system, with the rocky planets in the solar system, the diminution, the depth of the transit, the primary transit, when different planets cross in front of the solar disk, are tiny. They are, like in the case of Earth, 85 parts per million. So it's a tiny fraction, but we have nowadays the technology to measure these kind of differences. It's a very subtle work. It's something complex, but we are doing, I mean, in the future, we are going to do much better. And we are able to detect rocky planets beyond the solar system. But we do many more things with this kind of information. Because, as I said before, we have also the planet going behind the star. So we have a secondary eclipse that is related with the amount of light that comes directly from the surface of the planet. So we can have direct access to the properties of the planet. But also we have other characteristics in this geometry. When the light from the star crosses the atmosphere of the planet, when the planet is in front, there are changes because of the molecules and the atoms in the atmosphere of the planet. And just doing some simple arithmetical operations, but in practice, they are very difficult with the light that we receive from the star. We can analyze the properties of the atmosphere of the planet. This is called the absorption spectrum of the atmosphere of the planet. And then we can derive the composition and the geochemical properties of the atmosphere. We can do also other things. You have an example below. It's a Kepler 91, a star. It's a giant star, and we have this kind of bumps in the light curve, but they are produced by the deformation of the star. The planet is so close, and the external areas of the star are so, the density is so low that the gravitational pull of the planet can deform the surface of the star, and the geometry we see as the planet goes around is changing, so we see this kind of bumps. So it's an indirect way also to detect the presence of a planet and to derive or to have an estimate of its mass. So in this particular case, that I will describe a little bit better, a little bit more in a few minutes. We have a very interesting system because the planet is going to be engulfed by the star. So other method is the direct image. In fact, what we would like to have for most of these systems, it would be nice to have a picture. It's impossible for most of them because of the technology and the configuration of the systems. But we nowadays, with the current technology, we have been able to detect systems as complex as this one. Is called HR8799, that at least has 4 planets at distances that resemble in some way the outer part of the solar system. You have as a comparison below, but the planets that we have been able to detect are much more massive. But a note of caution, because the way we have to derive the masses here is just a crude estimate from a perspective, because it depends on theoretical models and they assume age. Because the final masses we are going to be able to derive will depend on the whether the system is very old, very young. This complex transparency, this complex plot, actually give you information about the first method that was used to detect a planet, a giant hot planet around a solar-like star. It was around the star 51 Pegasi, and we are using the radar velocity methods. The sketch provides how we can see the lines, the spectral lines coming from the star, how they shift in a periodical way because of the induced movement due to the presence of a planet. This is a very massive planet that has a very short orbit, very close to the star. It was a surprise when it was detected, because it's something that was not cannot be found in the solar system. So it was the first hint that our self-centered view of the universe again is being demolished step by step by the discoveries we have made. In the solar system is just one possibility in the landscape of the exoplanets. It's just one of the planetary systems and planets we find here. There is a limited sample of what we are finding far away. Other thing that is going to be, or the method that is going to be very important in the next few years is the astrometry, because as the star is moving in the galaxy, because stars are moving, there is a reflex movement due to the presence of a planet or several planets. These movements are very tiny because they are proportional to the mass of the planet, but with a satellite that was launched more than almost 10 years ago by the European Space Agency, EAI, eventually is going to deliver a catalog of several thousands, we expect several thousand planets that actually are going to be very complementary to other techniques. Techniques like gravitational lenses, this is a very exotic method. Unfortunately, this method cannot be repeated in the sense that it happens just by chance. And when the planetary system crosses in front of a very far away source, like another star, there is an enhancement of the amount of light we get from the faraway source. And with some mathematics behind, we can derive the mass of the star, of course, but also the spike that is due to the presence of a planet, or whatever number the planets would have the system. But as I said, in fact, this only can happen, well, could happen again by chance, but it's not a repeatable methodology. But in any case, we have now detected several dozens systems based on this method. As I said before, we have a very big diversity of planets. This plane represents the mass of the planet versus the orbital periods. And each method, like astrometry or transits of radar velocity, etc., essentially is proving different kind of configurations. Some of them are very good trying to discover massive planets close to the star, like the radar velocity, or others, like imaging, is very good with planets that are far away from the star. The bottom line here is that we have identified several families of planets, that they are located in different positions within the planetary system, but so far we have not been able to detect anything like the solar system. We have detected planets like those present in the solar system, Earth and super-Earth, or Neptune's or Jupiter-like. We have detected other types of planets, but the technology we have and the machines we use are not yet able to detect anything like the solar system. Eventually, with things that we are building or things which are going to be launched, like James Webb this December, hopefully, we will get additional information, but essentially James Webb is not prepared for the discovery, although it will, but essentially it's a machine that will be devoted to characterization. But eventually, things like Plateau, this satellite for the European Space Agency, will help with this side. So what kind of machines we are using? I'm going to focus just on a few things we have been using on space. One of them actually was one of the main drivers of the revolution, essentially for the transit spectroscopy, the transit the method, sorry, was the Kepler. Kepler is a spacecraft that was launched by NASA more than 10 years ago, 12, 13 years ago. And actually Kepler used two different strategies to discover planets. It was pointing to the same place on the sky for more than 3 years, and is the left-hand side plot you can see. It was the sky plane that was looking at was quite big, because it's a very important factor to be efficient, how much the field of view that you are using. But eventually, and it discovered many planetary systems, several thousands, but it had a technical problem, and NASA devised a new strategy, just pointing to very specific places along the ecliptic, a very specific positions on the sky, with pointings that lasted only 3 months each, but it contained very interesting astronomical objects. And here I'm providing in the right-hand side one example, because this field of view contains 2 open clusters. One of them is very old, M65, and the other is half, but M67, sorry, is about Earth age, and Precipice is much younger. It's like 600 million years. With this strategy, we couldn't do anything better because of the technical limitations. With this strategy, in any case, also Kepler was working for many years and also provided interesting information. Unfortunately, since it was not able to point for longer periods to the initial field, it had a limit on the kind of planets and the orbits that could study. Now we have other spacecrafts. One of them is TESS, that is you see the space coverage in the right-hand side. Essentially is studying the complete sky with different kind of coverage. There is an area that was studied for essentially 1 year in preparation of the James Webb Space Telescope, because its main goal was to provide golden targets, Earth-like planets, using transits. So the James Webb is going to be able to study these systems. And eventually, Plateau, that's going to be launched in 2027 or 2027, yes. And we are now studying different kind of configuration. What is going to be the strategy, the best strategy to point for 2 or 3 years to the same sky and the same point of the sky, or also to complement the strategy with much shorter visits to other areas. But the important thing here is that the area of Plateau is going to be huge, and in principle, it should be able to detect an Earth-like planet orbiting a solar-like star in a Earth-like orbit. So essentially, the goal is to detect Earth sibling beyond the solar system. And this is a compilation of the different spacecrafts we are using or we are going to use in the future. You see that we are using spectroscopy, we are using astrometry and photometry to detect and to study planets. We have this flotilla of spacecrafts, and in the future we are going to have even more. So the field is open to new, young, bright researchers, because it's going to be this golden age that I was talking at the beginning. It's going to be, in fact, it's going to last a long time. So we are going to be full of data. We are going we are really in adventure. We are, it's a fascinating moment to be in the astrobiology field, because so many discoveries, I'm sure, they are going to be done. It's going to be, as I say, fascinating. Anyway, some astrophysics to understand the context of the things I'm going to tell you about. This is an easy diagram, not so easy. I will try to highlight the main points here. The observables we get from a star depends on time. Essentially, we get the luminosity, the light is emitting to the space, and we can derive with different techniques the temperature of the star. With this information, we are going to derive many more things. And essentially, we want to detect and to study the characteristics of the planet or the planets in a planetary system. But this is important because the luminosity of a star or other astronomical objects like brown dwarfs or planets, in principle, they decrease with time. So it's a property that has to be taken into account when we try to understand the characteristics of the things we are looking at. Just to let you know, for those who are not astrophysicists, the difference between the stars and brown dwarfs is the source of energy. The stars are able to fuse hydrogen or other elements inside to produce energy. Brown dwarfs only do this in a very tiny fraction of time, but essentially they only do with a specific isotope of hydrogen, that is deuterium. And we can find even less massive objects, that are the planetary mass objects, to be redundant. that they don't have any kind of nuclear reaction at any moment. But the formation mechanisms is something that is still, we know many things about how they are formed, but still there are issues that are under discussion. And in fact, a planet that is formed as a planet could be expelled and to be traveling around just by itself. Or conversely, a very low mass object around Earth could be captured by a star. But unless we are able to have a lot of information, in principle, they are indistinguishable. There are things that we can do, but not many things, and not with the kind of information we can get in an easy way. So, sorry. So what we have found beyond the limits of the solar system, some taxonomy, using the techniques that I have described and other things that we have. We have found several thousand planets, and now we see that the crop from the transit technique actually has been the largest. Essentially, 3/4 of all the planets we have discovered come from this technique, and the second is radar velocities. And actually, they provide a lot of information. And when, as I said at the beginning, when we have both things combined, is when we get the maximum amount of information about the physical properties of the planet, but also we can go beyond, studying the atmosphere, etc. So this is the statistics or the historical view, how the field has progressed over the years. You see that the amount of planets and how different techniques are being more or less successful, they are evolving in time. And once Gaia, this astrometric satellite, releases its full sample of planets, then we are going to have, from my point of view, a much richer perspective of what we can find there. In any case, one very interesting result that now we know for sure, I repeat again one of the things, one of the comments I formulated before, is that there are different type of planets, and some of them are not within the solar system. At least we can find 8 families, and only the C and the blue are in the solar system, and there are other type of planets in between that we already have identified beyond the limits of our home. And the most striking result is that the most common planet, at least with the techniques we are using, are not present in the solar system. It is something amazing. I think it came as a surprise, and is something that will be confirmed in the future, hopefully, and it needs a full explanation. In any case, when we combine different properties, when we combine what we know about the mass of the planet and the radius, then we can confront this information also with models, and we can have a first understanding of the composition, not the density, but also the composition of, sorry, because this is in Spanish, I thought I translated everything, but I forgot this one. I apologize for it. In any case, we can see that essentially the planets we are finding, they follow essentially what we find in the solar system, but not quite when we have a look into the details of this map. One key point here is errors, how we treat errors, and I'm going to discuss it. Several of the spacecrafts that we are sending, like Kepler, for instance, the goal is to get these values with much better accuracy, trying to diminish the error bars, because the comparison with models and the interpretation of results heavily rely on how important these errors are. In any case, here you have radius and masses confronted with the distance to the central star, the hot star. So again, you see that the solar system is not a characteristic. The planets that we find here, they are not common, both in terms of mass and in terms of the disposition, the hierarchy within the planetary system. To build these plots has taken several decades and a huge effort by a lot of people, but now we are filling these gaps. And I again emphasize that eventually, once we get in this decade additional information from Gaia, Plateau, etc., and all the information that the James Webb is going to provide, I'm pretty sure we are going to have a almost full understanding of many of the questions that I formulated at the beginning of this talk. One of the most fascinating, and I am biased here because I was involved in this research, one of the most fascinating planets we have discovered is the Kepler Native one I mentioned before, because it goes around a very big star. It's a giant. It's a star that is going to die eventually. But all the stars are going to die, but this is at the end of the evolution. And the planet is so close to the star that actually, essentially, more than 2/3 of the surface of the planet is illuminated by the star, because it's so huge and it's so close that also probably there is both the objects, the planet is locked, and the same hemisphere of the planet is looking at the same hemisphere of the planet is looking at the star. So the characteristics, the atmospheric characteristics of this planet, probably are very interesting because of all the things, like the circulation of movements, etc., that could be studied. Anyway, going to the atmosphere, just to give you a few details. Now that also, to me, came as a surprise, we are able to have a look at the chemical composition and the physical properties of the atmospheres of a significant fraction of these planets, using this technique that I mentioned before, the absorption spectrum that is produced when the planet crosses the disk of the star. So we have detected a collection of, I'm going to give you a sample, it's not complete this list, several atoms and several molecules. Some of them are very significant. They have a very interesting astrobiological components because they are the very basis of life. And in several of these several of these planets, we have detected a large number of features, molecules and atoms. And one of them, for instance, already we have been able to identify 16 different types of chemical molecules. So this is a first step. Once James Webb starts to produce results in 6 months from now, I think that we are going to have a complete view of this kind of diagrams in terms not only of errors and precision, but the comparison with the models and the information we are going to be able to derive. This is not the only thing that we can obtain from the atmosphere. We can also obtain the profiles, atmospheric profiles, but this is always with comparison of with models. So again, the reduction, the improvement of the errors of our data is key to be able to actually do a proper interpretation of the information we are getting. So we go to interiors because we also can have some interesting information, and I'm going to show you a couple of diagrams like about these tethering diagrams that in the case of the gas or ice giants, we can have with the confrontation with models, we can have a knowledge about how is the proportion of different components, and the same can be done also for the rocky planets, how much silicates and water and iron essentially they have. So these are amazing results, and we can have also a comparison with the interior composition of Earth. This kind of comparisons depend, of course, on models, but it's just, I would like to emphasize that we are crossing the boundaries between different disciplines, because this is this is not astrophysics, this is geology. And we are starting to get into the point that we can have exogeology, if you want to call it, for instance. I'm not going to describe formation, just to give you some examples of what we can see now. These are real image of a planetary system information. It's a town that was obtained with ALMA. It's an interferometer there. This in Chile. Planets, stars, and planetary systems are formed from molecular clouds in a complex evolution. But now, using different kind of techniques, but essentially most of the data is coming from ALMA, that is providing a revolution also. We are getting this kind of pictures. So it's the disk of the circumstellar disk that is forming, essentially showing us how these planetary systems are being formed. And actually, we can get now that is really, really surprising. This is a very nice disk around a very low mass star that has at least 2 planets. You can see here as a B and C. There are Jupiter-like planets, and we know, because we can see the blue picture. We can see that using special techniques, these 2 protoplanets emit in H-alpha. This is an important line in the spectrum, and it's because helium is falling into the planet. So these 2 planets are still in the process, in the formation process. They are gathering gas from the environment. And this is something really, really amazing. I don't want to repeat myself with adjectives, but it is so surprising that we are able to see this thing in direct. Some planetary system taxonomy. Essentially, we have a similar diagram when we compare with the planets. This is just for the planetary system, multiple planets within a system. But the methodology that we are using to discover them is the same, of course, and they follow the same pattern. I have shown you this diagram, but just to give you a different view, when we put in this diagram information of other planetary systems, what we get is something like this. This is the mass versus the orbital periods. And in different colors, you see different families of, not different families, different planets within the same planetary system. So we are having multiple planet systems with 6 planets. For instance, TRAPPIST-1, it has several, actually a significant number of Earth-like planets, in light blue, for instance. Or we have hot Jupiters, like WASP 18, that has a Neptune-like planets, and both of them are very close. It doesn't mean that it doesn't have other planets beyond, because our techniques are limited. But in any case, what we are seeing is that there are hierarchies and distributions very different to the solar system. The solar system is just a possibility. So additional results, just to show you the complexity and how we are improving. This is data coming from KERPS, a European satellite. We see the light curve in the left-hand side, 2 planets, the dips produce the planets. In some cases, these dips are combined because both planets are in the light of sight. And to be able to decompose this information it's not very complicated. It needs some exercises and some work. And in this particular case, we were able to discover the F planet and to reduce the errors of the radii of each planet. So it's one of the goals that is needed to be done. One of the tasks is to reduce the errors. Or, for instance, to detect several super Earths around one of the stars that eventually is going to be studied. I have you have seen on the diagram like this, the radius versus the mass. This is just restricted to super Earth-like planets. And you see that when you are able to reduce the errors, then the knowledge about the physical properties of the planet really improve. And finally, one of the most curious is this system with six planets, but they are in resonance. So it means that the configuration is repeated after some time. And it's something that has very interesting information about the formation and evolution of the system. So I'm going to discuss briefly a few results. The first one is the habitability, because it's one of the things that we want to know, whether these planets have the proper condition for biological activity. You have seen several versions of this plot. When we can say now that we have discovered a significant number of planets around the habitability zone, but one thing we have to discuss and to define is what we mean by habitability. In a very restrictive perspective, then we would have a limited sample, but things could be better because different phenomenal volcanism actually enhance the area where life could at least survive. It's another version of the same thing. And since we have information about the density of these planets, then also we can have additional information whether a planet, in fact, could have the properties to harbor life, at least to sustain at some point. In any case, as I said, there are several additional characteristics we have to take into account. One of the things, for instance, is whether additional properties for the planet itself could allow the presence of biological activity. And for instance, a few months ago, a new kind of planets, they are very massive with a huge amount of water, but with hydrogen, molecular hydrogen atmosphere, in fact, could have the proper conditions to have life. And in fact, this would enhance in a significant volume the area around a star where you could find life. Finally, one thing you have to take into account is also, again, the properties of the star. The stars are very complex objects. They need not only in visible light, they need also in the X-ray domain, the ultraviolet, etc. And these properties also evolve with time. You can see here a sample of stars in the solar neighborhood that they are very well studied, and how the coronal activity changes with time, and this has a direct implication on the properties of the atmosphere of the planets around and the possibility of habitability. So the connection between the star and the planet is really important. Just to end, here again, I would like to emphasize the role of Gaia and other instruments like the ELT, the telescope, the European telescope that is going to be finished in a few years in Chile also, because each method, as I said at the beginning, is probing different kind of planets in different configurations. So we need to use different instruments, different setups to be able to study and to identify, not only to identify, but also to identify, to study the characteristics of planets and the planetary systems as a whole. And of course, the final goal is to be able to identify a solar-like star, a solar-like planet, or a Earth-like planet with biological activity. So I would like to end with the words of Anaximander, that he was a Greek philosopher more than 2,500 years ago, who probably was the first one to propose the possibility of worlds beyond the solar system, together with Lucipos and Democritus, that normally they are the first to be mentioned. And with this, many thanks for the talk, and I am open to questions.